Sounds happy where you are.
Oh, you can hear that? Yeah, the kids are running around somewhere. I may have to mute myself if they come closer. But the baby's in the room where I normally go with Caitlin, and it's too cold to go outside. So
Yeah, right. What's the baby's name?
Ben.
Huh?
Ben.
Ben. Oh, Ben.
Yeah, he's 5 months old now. Yeah, 5.5.
Evening all.
Evening.
Hey, KP.
KP sent me a message saying that he has an escape plan. If things start to, get too many questions he can't answer.
What's the escape plan?
Unfortunately, it doesn't work on Linux.
Oh, I see.
Oh,
really? That's surprising. Yeah.
Well, it needs a thing that only has Windows and Mac drivers or something.
It's called Zoom Escape or something like that. And you click on it, and it starts to says, oh, my reception is bad. Oh, I have to, you can't hear, I can't hear you.
It has other sound effects too, like somebody urinating.
It's a bit like that. Was it Saturday Night Live? I think they had a sketch where it was a special delivery service, right? Where if you're late, you just get that company to deliver the package to whoever it's supposed to go to. And the only thing they're good at is excuses. So oh, well, we sent it on time, but no, it's not there yet.
I think I've done business with that company.
Right. I was going to show off my cookie, KP. I'm not a very good cookie. I was going to build a whole bunch of this pre-mixed. I was going to make one great big one. Let me see. Did you make a big one? Oh, a bowl full.
No, I couldn't be bothered. I bought some.
Yeah. Oh, you bought some. Yeah.
I was going to say, is it not very good because you got the date wrong? It's been sitting there for a week. Waiting on.
So where's Peter? Peter is the one who said we have to join the meeting early so we could all socialize. You know what his secret plan was? On the day he talked, he just wanted extra time. That's all it was.
Hey. He did email me a day or two ago with a question about your talk, KP.
Wait a second, Jerry was asking.
Sorry, Jerry.
Go ahead, Jerry.
I wanted to know how the vaccines are going in the Netherlands. I heard on the radio they were behind.
Yeah, they get them in there behind. That's right.
They're not very fast, but Eva and I are going to get our first shot on Thursday.
Ah, good.
And then we'll have to come back for the second one.
See, I had my second shot March the 2nd.
Yeah, but you're a bit older.
Well, that's right. I had to get in with a 65 and older crowd. I missed the first kickoff.
You snuck in there, eh, Jerry?
I thought about it, but
started at infinity and then counted down.
Okay.
I haven't used a fake ID since I was, 20 years old and wanted to drink a beer, but I didn't think it would work in this case.
Yeah.
Can't really pass the 65. Hi, Peter.
You're going to be knitting something, Lynn?
How did you know?
Facebook.
Hi, Lynn.
Oh, that's right. Yeah. 3 of us went in on 150 balls of yarn. So COVID.
3 people, 150 balls. Wow, that's.
Yeah, it's almost 50 each, you know?
Almost.
What do you want all that yarn for?
I'm a knitter. I'm an avid knitter. Actually, I got a couple projects going on right here. Just finished this pillow.
Oh, nice.
And I've got a couple sweaters going. Yeah, it's just nice to have a lot of color options.
No Hayden yet. He's haven't heard from other than Joe, our Pembroke folks. Eh?
I'm at home, so I don't get to see them anymore. I don't know what they're up to.
Right, right.
You suppose, what's his name, is still working on his kitchen?
Yeah, I was going to say, Lazo said he would start attending when his kitchen was finished, right?
It's that one drawer that's been sitting on the floor for months now.
Mm-hmm. Reminds me when I was in Sicily, and let's hope for the best for the folks in Sicily near Etna. That's where I was. Angelo
Ooh.
Bella. He was
Mm.
driving me around, and it was kind of interesting on the hillside whatever of Mount Etna. There's all these houses, and none of them are finished. They're all their roofs have scaffolding on them, and none of them are finished. He explained that was because until you actually finish them, that your taxes don't go up for your second story. So they never finish them.
By the way, my Facebook photo has me with Angela and Conchetta up on the crater of Mount Etna.
Yep, he took me up there. Yep.
Oh, very good, very
Yep.
good.
Yeah.
Now I'm told that people are just barred from going up there.
Well, yeah, because it erupted, right?
Yeah.
Well, it's kind of dangerous.
Yeah, but at that time it was also erupting,
Yeah, but
except on another side of the mountain. So
Oh, I see. But I think this time, apparently, according to my news source, which is my wife, it's very dangerous this time.
It was smoking a lot when I was there.
Yeah.
And we stayed a couple of days in the little town, I believe it's called Carolina.
Hmm.
That sits right on not on the edge of the crater, but right on the edge of the mountain, Etna.
Yeah.
yeah, when I was up on the crater, I was dodging those clouds of sulfur dioxide pretty often, but it was a great experience.
Right.
Absolutely unforgettable.
It's a treacherous walk, right? All the stone is very sharp edges. And
Did you see the footage from Iceland?
You walked away from it?
what's that, Jerry?
So I asked Peter, what made it so great? Just that he walked away from it?
No, it was just a fantastic view, and it's a unique place. It's completely unlike any other place I've been in.
Well, we should get going, or else KP will run out of time.
I will run out of day.
Yeah, that's right. Was it 11 there? 10?
It's a little over 10, a little past 10.
Yeah. And you're not oh, you are daylight saving now, right?
Yeah.
Yeah.
We're in the same frame of reference now.
Yeah. Well, Will, did you set the thing for multiple hosts?
Oh, no, I don't think that I did. KP, let me set you up for sharing, and then you can go ahead and get started. All right,
I like
you're
your
now the
mug.
host.
I like your mug, KP. I've got a brother for whom it would be very appropriate.
Well, this
That's
is from the
old
car
car
talk guys.
That's the old Car Talks slogan, yeah.
Yeah.
Don't drive like my brother. Yeah. Well, all right. Oh, suddenly I have way more things to, more buttons. What?
Yeah, for a long time he drove with a broken speedometer, and so he would be going up to 90 miles an hour without knowing it.
Wait, okay, I have to activate the window.
And you're giving us a talk on computer science? Is that what you think?
Well, not quite.
There we go. Machine learning. Yes. Okay.
And I'll try to make this a bit bigger. So I'll probably obscure you guys. Wait a minute.
That's only to you. I think we see our own screen shows us the pictures, the videos.
Yeah, but for a
It's
second.
big enough. I don't know. Anybody need it bigger?
Yeah, I need it bigger on my own screen.
Okay.
What the hell did I do usually? Okay, well, let's see if I can get it going like so. Oh yeah, wait. No, presentation.
That'll
There we
do it.
go.
There we
Oh,
go.
it's fuller screener for me too. Let's see. Yep, that's right. Okay. You can hear me all right?
Yep.
Fine. Okay, so this is something that I think Todd is to blame for this because he posted a link to this on Facebook some time ago. And where the link led to was this. It was a thing in Nature.
Wait, hold on. You moved on too fast. I couldn't even understand half the title.
Which one?
The second half.
The subtitle?
Yeah.
That's a setup for a joke at the end. And this is the outline of the whole story. I'll get back to the subtitle at the end, don't worry. And some of you old timers may know what it means already because I've used it before. Anyway, this is what I saw, and I was sort of excited because I don't know if you can read it, but machine learning leads mathematicians to unsolvable problem, and then it sounds like this is going somewhere to the incompleteness theorems or something like that that Gödel used. I used the Liar's paradox for the first incompleteness theorem. So I thought maybe that was an impossibility like that. Okay, then I read this note. This is not the paper itself that I'll be talking about. It's sort of an attempt at explanation what the paper in Nature Machine Learning was all about. So the actual journal was a subsidiary of Nature. And but anyway, this thing in Nature told me what the paradox was that the machine learners stumbled into, a paradox known as the continuum hypothesis. And I was like, wait, what? So I read this whole piece and I didn't get any wiser. It was talking around the continuum hypothesis, talking around what was happening in the actual paper. So I looked up to see what actually was in the paper. And it was sort of interesting because I think I'll be able to talk about it for a while. And I actually wrote a comment on it, which I sent you the link last week. So what's in the paper? Well, it's about machine learning, apparently. And machine learning needs functions to help train whatever it is that is being trained at that moment. And in the paper, you'll find that the existence of a certain kind of learning function is equivalent to this. So it's not quite the continuum hypothesis. It's sort of what you would call the weak continuum hypothesis. Weak in the following sense. Well, here is a quote from, I think this is the paper where Cantor proved that the unit interval and the unit square or all unit cubes have the same cardinality. And towards the end of the paper, he was talking about comparing sets according to numbers of elements, so to speak. And this is actually sort of the first time that the continuum hypothesis appears in print. And for those whose German is a bit rusty, he promises that by some inductive method, the method which we will not go into right now, we will get closer to the theorem that the number of classes, and the classes that he's talking about are equivalence classes according to cardinality. So the Einteilungsprinzip is the division according to cardinality. And the number of equivalence classes of the subsets of the real line, linear manifolds, linear sets, is finite. Well, this is saying that there are only finitely many possibilities for cardinalities of the subsets of the real line. So Cantor said this, but he specified that finite number, and he says there are only two equivalence classes. So that's the moment that the continuum hypothesis, or at least his continuum conjecture, supposition, entered the literature. Okay, that was one sentence and the explanation of what Cantor said. In a bit more detail, I'll try and sort of describe what the problem is all about. The paper is sort of typical of many things in applications that I see. I get all excited about something being applied, and then the example that is given is usually quite simple and not very informative. And then in about 2 or 3 lines, things get very abstract, and that's the same thing what happens here. The problem was illustrated by, say, an advertising website or something, well, placing advertisements on websites. And what's the problem? Well, you want to pick a finite set of ads to put on the paper for the person that is visiting the website. And you want to maximize a certain expected value. Well, the expected value being the interest of the ads to that visitor. Of course, you cannot always find the maximum, say within a certain tolerance, within epsilon or delta, whoever is more important there. The difficulty in the whole thing is that you don't know what the probability distributions are. Now, this problem is finite, very finite. You have finitely many companies that can advertise on your website. There's finitely many people on Earth, so you can only expect finitely many visitors. But what you see happen, and it's what we do in our analysis courses as well, or what we do in mathematics, when the number of points gets too big, we simply replace the set of points by the unit interval or unit square, and we treat the problem as a problem on the continuum. And that is what our friends did as well. So from a family of finite sets of a potentially pretty big but still finite set, they make the jump, I was almost going to say to hyperspace, to the unit interval, and work there. Try and see what happens there, and then maybe translate it back to the finite case. So what do they want? They want a function of this nature. You want to take they want a function from the union of all the unit cubes to the finite subsets of the unit interval, and they wanted to have certain properties. And I'll write down what they want and will not refer back to that anymore, because there is a way more set theoretic translation of what they actually want, and that's what we all understand and what we can work with. because they want to mimic, or I don't know, simulate finite sets. They look at all probability distributions on a unit interval with finite support, which is a pretty big collection anyway. And every finite set of the unit interval has an expected value with respect to those distributions. And of course, if two finite sets, if the support is disjoint from the set F, then the expectation is 0. But it might hit F, it might not. Anyway, the optimum for a possible distribution would be the maximum expectation that you can get given all the finite sets. Well, if you have one distribution, you only look at the finite subsets of the support, because those are the only ones that can actually give you something. And so for an individual distribution, this is easy to calculate if the support is not too big. But the objective of this G is to sort of be uniform over all this P. So the function G has to take all the P's into account somehow, which is a pretty big ask. And here is the, let's see, no, here is the formula that looks pretty impressive, but you can sort of translate it. The EMX stands for estimate the maximum. The epsilon and the delta are the parameters. And a good function, an epsilon delta learning function, is one that it works only on 1 power of the unit cube. The power depends on the epsilon and the delta that you ask, such that if you start to calculate all the expectations of all the points in that n cube with respect to the product distribution of all those probability distributions, you want the expectation to be below the optimum for the distribution minus epsilon, not very often. The probability that occurs should be smaller than the delta. So this is sort of a probability measure on probabilities, because you want for very, very many probabilities to be quite close to the optimum of that particular distribution. It looks pretty impressive, and I didn't actually dive into that very deeply, because fortunately in the paper there is a translation to our kind of combinatorics. You can look at this question for all possible epsilons and deltas, but in the paper they only look at epsilon and delta equal to 1/3. And then there is such a function if and only if there is an m+1 to m monotone compression scheme for some natural number m. And what the hell is a compression scheme? Well, it's this. You can almost guess what it should be, but maybe not quite. K and L are natural numbers. And what you want on the L side is a function, well, from the L element subsets of the unit interval to the finite subsets of the unit interval. So okay, this is kind of a set of L advertisements if you want to go back to this website business. And the finite subsets would be something like the customers that should be interested in what in the stuff advertised for the in those advertisements, and you want to be able to capture k-element sets of customers with your L many advertisements. It looks a pretty, it looks like, it sounds like stretching things a bit, but this is the best interpretation that I can give if you want to make this sound applicable. And what do you want? Well, you want for every k-element set, you want to know that there is an L-element subset of X itself that captures X. So the ads that go, the ads that the people interested in Y should contain X. But you want to be able to do something like this. But let's forget about the interpretation. This is just a combinatorial thing. You want to be able to find a function like this. You want to associate to every L element set some finite set. And for every X, you want a subset Y of the cardinality L such that X is captured by that particular subset Y. Okay. Let's reformulate this a little bit, because you actually have an implicit function here from K to L. Because what it says here, for every X, there is a Y such that X is captured by the eta image of Y. Well, there is a choice function there apparently. For every X, I can choose a Y, let's call that sigma X. And such that, well, okay, sigma X should be a subset of X because that's what the Y is supposed to be. And X should be captured by eta of sigma of X. Fine. Now, the sigma is not really explicit in the paper, and the paper does make things too difficult here and there. But you can do away with the eta. There is such a scheme, there is such a function, if and only if there is a finite to one function from the k element sets to the L element sets that picks a subset. All right, so every X, so every Y here is picked by only finitely many X's. Now the question is there such a set, such a function? Well, okay, let's prove the if and only if before we go to the question of existence. Why is the sigma that we choose with this property is automatically finite to one? Because if sigma of X is equal to Y, then X should be a subset of eta Y. Well, eta Y is finite. Eta Y is only finitely many subsets. So Y is the image of only finitely many X's. If, well, if you have your sigma, you can define your Y using the finite to oneness by simply unioning up all the X's that have Y as their image. That is a suitable eta. Remember, there was no bound on the cardinality of eta Y. It just had to be a finite subset of the unit interval. So where are the cardinals, you might ask? And well, here they are. The theorem, there is a theorem in the paper, and that's pure set theory. You take a set, you take a K, and we have a finite to one function sigma from the K plus 2 subsets of x to the k plus 1 subsets of x with the property that it always chooses a subset. If and only if, wait for it, x is at most L of kappa many points. So this is a characterization of Aleph kappa. It seems like it doesn't say anything about the cardinality of the set, but it does. And there you have it. If there is, I mean, this thing, this function sigma here, determines a k plus 2 to k plus 1 monotone compression scheme, as we just saw with the if and only if thing. And so if we want an m plus 1 to n compression scheme for some m, we want this to happen. We want this to happen for that m, and that means that we want the unit interval to have at most, I don't know, Aleph m minus 1 points or something like that. And so if we want it for some m, we want the unit interval to have cardinality less than Aleph omega. So that's where the continuum hypothesis comes in. And that shows you the undecidability in the machine learning thing. Because
does it also say you can't do it for Aleph 1? I'm trying to read that. I'm sorry, if the unit interval has size Aleph 1.
Well, then you can find it's if and only if. And so.
Well, sorry, I was thinking of the cardinal. Never mind. I take it back. I'm being dumb.
Well, there has to be a first time for everything. Anyway, when I read this, something was sitting in the back of my mind, and I knew there was something Aleph K-ish that I'd seen before. And well, here it is. There is an old result by Kuratowski, 1951, as you can see, that also characterizes Aleph kappa. It's like, it goes like so. And this is also what I put in the paper that I wrote about it, because it's, there's a nice circle of equivalences, and it's a nice exercise in a bit of the combinatorics of the first uncountable cardinals. Anyway, the same power, x to the k plus 1, x to the k plus 2 is in play here. And you can partition the k plus 2 power into k plus 2 sets, such that for every, I think I had no, I thought I had a pause here. For every I, you look at AI, and you look at every point in the power. You look at the points in AI, no, sorry, the X could be anywhere, but you look at the points at AI that are equal to your point except at the ith coordinate. So here is my point X, and I can change it in one coordinate, and I'm counting the number of times I end up in AI, and that should be finite. Well, this looks maybe a little bit strange. Okay, Kuratowski said AI is finite in the direction of the ith axis. So every section in the direction of the I-axis is finite. Let's look at n squared. Well, here is your division. Everything above the diagonal, everything on the diagonal and below, or vice versa. finite, 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 finite in the direction of the 0th coordinate, and finite, 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 finite in the direction of the first coordinate. So there's no problem there. But if you go to k, k is equal 1, then it's already non-trivial, and you will also see that in the machine learning paper. Kuratowski and also the guys in the machine learning thing prove it by induction, that statement that I just had over there. So the existence of the k+2 to k+1 map being equivalent to x being at most Aleph k is proven by induction on k. And the same thing is what Kuratowski did. And it's kind of nice. And I want to show this because I have some comments about the results of the paper later on. So how do you make the 3 sets in the case of omega 1? So, well, you know that if I take the same picture here and I use omega 1, then I get countable, countable, countable on all vertical lines, and countable, countable, countable on all horizontal lines for the A0 and the A1. And actually, there are some comments by Kuratowski on this type of thing as well. But so how do I get that finite in 3 directions if I'm looking at omega 1 cubed? Well, what do I do first? Well, I use the inductive assumption and I take a splitting of every countable square that I meet on my way to omega 1. So okay, when I split omega, that's fine. I use the A0 and the A1 I just had a few moments ago. But when I get higher and higher and higher, I have to make this splitting more complicated. I cannot just use the normal ordering because then I get countably infinite lines, horizontal or vertical. So this picking and choosing, well, we do it simultaneously. So we use the axiom of choice here. Nothing wrong with that. And then what do? Well, here is the construction of A0. What is A0? Well, we want, for an arbitrary point, we want only finite variation in coordinate 0 when we hit A0. And so what do we look? Well, we take the maximum of the 3 coordinates and we look, if it's beta, then we look at the 0 part of the partition of beta plus 1 squared, and we want alpha comma gamma to be in there. If the maximum happens to be gamma, then we simply switch beta and gamma, we switch their roles. Why does this work? Well, implicit in this definition is that because we only put a triple into A0 if the maximum was the 2nd or the 3rd coordinate. Okay, and an extra condition, but the first step in putting something in A0 is the 2nd or the 3rd coordinate is the maximum. And then we only look at points in the B0 thing. And well, yeah, if we fix the beta and the gamma, we get only finitely many alphas. And we get only finitely many alphas in case the roles of beta and gamma are interchanged. So when I fix my beta and my gamma, I have only finitely many alphas below that maximum that put me in A0. So this set is finite on the 0th coordinate. And well, you can guess what the other two are going to be. A1 means either the first or the last coordinate is the maximum. And A2 means coordinate 0 or coordinate 2 is the maximum. And in the last one, coordinate 0 or coordinate 1 is the maximum. And if you understand the case k equal 1, you understand all the other cases as well, because you basically do the same thing. There is a connection, of course, between this finite to 1 mapping and the partition of the powers of omega k. In general, when we identify a finite set and a k plus 2 element set, we identify it with a point in x to the k plus 2, where we assume we have some linear order. Well, omega k certainly has a linear order. And we can actually construct the function sigma from Kuratowski's decomposition. You take a k plus 2 element set, you identify it with its enumeration, and you check in which set it is, and you leave out that particular coordinate. So that's the k plus 1 element subset of X. Leave out the coordinate pointed at by the set it is in. That works. If you have a k plus 1 element subset, it can occur, well, as the end of a point. It can occur as well, the first element of a point, or, I mean, the y can be here, or it can have its first element here and the rest here, and so on. And of course, all the way to the end, it could be the initial segment of a k plus 2 element set. But Kuratowski's demands tell us that we can only put finitely many ordinals here to put it into A0. We can only take finitely many ordinals here and get it into A1, and so on, and so on, and so on. And that means that ultimately we have only finitely many sets that will give us y as their sigma value. And actually, a k plus 1 doesn't really enter into this discussion. You never end up there. But that's only because we chose this monotone enumeration of the finite set. Now, there is a further connection. Suppose you have a compression scheme on omega k plus 1, and okay, of course, we only look for the case k plus 2 and k plus 1 here, but you can look at an arbitrary compression scheme. And well, either you take a countable element, or you take an elementary substructure of size omega k, or you just do some honest toil and take a closed unbounded set that is closed under the inverse. That means if y is an m element subset of member delta of C, then every x that has it as its image should be a subset of delta as well. Well, because sigma is finite to 1, so that can be arranged. And then you can define an n-1 to m-1 scheme on delta. And delta is cardinality omega k, L of k, of course. So you can take a compression scheme and push it one down if you want, if you will. And now what happens? I'll tell you.
So, sorry, was that by induction? We can do it for every N and M? Is that what?
No, this is going to be part of the proof that if there is a scheme, then the cardinality is at most ALFK plus 1 or K, whichever. We'll see in a moment.
Oh, I see. So we suppose that there is a sigma that works.
Yeah,
Then we get a reduction to working
smaller
for one
cardinal.
cardinal,
and smaller.
one exponent down and cardinals down. Yeah. Okay. Sorry.
And you will see what happens if we do the suppose not in a moment, because the theorem that we have, of course, because we can combine Kuratowski's theorem and we combine the compression theorem and say, here it is, but we can actually go around, because Kuratowski proved 1 to 2. We just proved 2 to 3. And we also just gave the key lemma for proving 3 to 1. So how do I prove that X has cardinality at most LFK? I assume it has cardinality LFK plus 1. For suppose omega K plus 1 does have a compression scheme like this, then the previous slide says omega K has a compression scheme like this. And we just we keep going down these stairs. And in the end, we will find that omega 0 has a 1-to empty set compression scheme. There is a finite 2-1 function
I'm
that
joking.
sends all the singletons to the empty set. Which is sort of impossible because it's infinite to 1.
And I realize the compression, the image could be a less equal. It doesn't have to be equal to that size, right?
Right. Anyway, there are other equivalences actually, which I realized when I was preparing this talk, and I'll go through that just quickly. In the 1980s, I think 1984, if I recall correctly, Cichon and Moraine, yeah, he's also Polish, so I'm trying to figure out how to pronounce this in the Polish way, but they proved that continuum at most Aleph kappa is equivalent to sort of piano mappings, surjections. The papers don't say continuous surjections, but I suspect they are continuous, that are almost kind of differentiable. You can find continuous surjections from RK to RK plus M, and M could be 1, 2, 3, 4, 5, whatever. And you can have at every point at least K of the coordinates be differentiable. In particular, and this was an earlier result of Moraine, CH is equivalent to the existence of a surjective map from the real line to the plane, such that at every point, one of the two coordinates is differentiable. Which is kind of cute.
So by that you mean fix a value and then let the other coordinates range, or no, just let that one coordinate range.
What do you mean?
What does it mean to say one of the coordinates is differentiable? What does that mean?
Well, so F of X.
The derivative in that direction.
No, it's like F has two coordinates. And so for all X,
Uh,
Because if you look at, say, Peano's original map, that's as non-differentiable as it gets. It has jagged edges all over the place. So, and there is no way you can make a continuous surjection onto the unit square, say, that's differentiable everywhere. But what you can get, if and only if CH holds, is a surjection such that for every x, at least one of the coordinates is differentiable at that point. So okay.
and for higher k to k plus m, we just mean individual coordinate, or not a multi-dimensional version of the derivative.
So here, the f has k plus m coordinates, and you give me a point in RK, then k many of these
Yeah.
differentiable at that particular point.
Yeah.
And it's a, like I said, the proofs use these decompositions to actually, I think, to keep the history small enough to preserve those differentiable, the differentiability and the limit.
Well, it's interesting that you can see the decompositions used to give the existence, but the existence of the function giving the decomposition is also very interesting, isn't it?
Yeah, I must confess that I haven't read that paper in detail, so I don't know what makes it tick.
I was going to do my Eric there.
Well, that's one of the Zoom escaper sound effects, I think.
Yes.
Whoopee cushion. Anyway, when I was reading that paper, I thought, this is, to quote Car Talk, bogus. And that they're talking about machine learning, and that means, at least to me, it means that you got to have some sort of algorithm that tells you what to do. And so that function G that we were talking about should be programmable or whatever. It should have some concrete description. But if you go through, if you go through the proof and say, well, okay, let's assume the continuum hypothesis and then we can do machine learning. Well, yeah, right. You get a function, you get this compression scheme, but the compression scheme is really non-constructive. Then you translate it into a function G that is also non-constructive. So what good does it do? And I was thinking a bit about this, and I thought, well, can we have nice compression schemes? Well, how nice is nice? Well, for us, nice could be continuous, Borel measurable, or even Lebesgue measurable, even though that is occasionally quite wild. But let's say continuous or Borel. Well, there is a highbrow answer. No. And the highbrow answer is, suppose you have a compression scheme that is Borel. We have found one, we have constructed one. Then all I do is add Aleph omega plus 1 Cohen reals and kill it. By absoluteness, it's still Borel and whatever, but now it doesn't work. And so, okay, that's the highbrow answer. If you don't like Cohen reals and whatnot, you can do it quite elementary, by the way. If you have a compression scheme, supposedly, then actually, and I'll illustrate this just in the square. Remember, we were talking about, in this case, we were talking about 2-element sets, right? So here is a 2-element set. It just is a point with 2 coordinates. And suppose the compression says take this coordinate here. Well, here is the other coordinate, the one that we didn't take. Now we take a very tiny epsilon and we take a very tiny delta, such that the continuity tells us whatever we choose here, it has to be close to the choice that we made here. Well, it means that on this whole disk, we still take that that 0th coordinate. It means that the set of points above the diagonal where we take the 0th coordinate is open. The set of points where we take the other coordinate is also open. And we have 2 disjoint open sets in a connected space. One of them is empty and the other is everything. And that means that we are forced to, well, do this. Well, that's definitely not finite to 1. That's the main lemma. Well, and I just indicated what the main, how to prove the main lemma. And if you take if the thing is Borel measurable, then the above is almost true. If you use the, what is it? The Kuratowski-Ulam theorem about, okay, a Borel measurable function is continuous on a dense G delta. And then the Kuratowski-Ulam theorem says that on one axis, very often, the vertical section is second category or probably even residual. And when you combine that with that main lemma here, because this still goes through, the proof that I gave, as long as it's continuous on a subset, we still get an open subset. But now we have an open subset of a Borel set, so it need not be everything, but it's going to be it's going to take a big piece, and we get a non-meager set and 1x that is chosen very often, way more than finitely often. So, so now the thing is, one thing I know, the construction of the compression scheme from that learning function that we saw way at the beginning is quite concrete. There is a little bit of picking and choosing going on, but if the map G is Borel, you can use linear orderings that are Borel on the n cube to choose the first whatever it is that you need, and the result is a Borel measurable compression scheme. There's no big deal there. And so to me, at least, I would have said that the title of the paper should not have been Machine Learning is Undecidable. This particular kind of machine learning is just impossible. Because at least the translation tells us that it is not, cannot be done. On the other hand, that's also the title of a subsection in my in the paper that I wrote about it. The problem is finite. If you want to simulate a finite problem with an infinite set, you could use the rationals. There is enough rationals to go around to do this kind of thing also. And of course, we have a 2-to-1 compression scheme on the rationals. You order it in type omega and you take the maximum, and that was it. And now Will The subtitle of my slides says unencumbered by expertise. And reflecting the subtitle of the slides, I have no idea what that means for that function G. I haven't looked into the back construction from the compression scheme to the G to see if that actually works, say on the rationals in some sense. It referred back to some other paper. It wasn't, the proof wasn't in the paper itself, the Nature paper, but they referred back to something in a book. I looked it up, but it was a bit too long for me to actually dive into it. But there is a way to get from the compression scheme to those learning functions. But I'm not sure if that uses actually the unit interval somehow, maybe some compactness argument or whatever, or whether you can do this by hand using, say, the rationals. The compression scheme on the rationals is quite simple. You pick one coordinate in sort of a uniform way. And so I have no idea whether that actually gives a sensible learning function. It might give an algorithm, but the algorithm might be not very specific. I don't know.
Could it also be minimizing the output rather than maximizing the output?
Who knows?
Yeah.
There was somebody who wanted to do some project with me, and I was once going to assign them to read that construction and explain it to me, but there were other things that got in the way. But maybe I'll get some student to have a look at it once, because it looked accessible to that. I have no idea whether this is a sensible suggestion, by the way. And so if you want to read up on this, there's 1, 2, 3, 4, there's 5 authors for that learning paper.
Oh, I know Shai Ben David. I know him. He was a student of Shala. Yeah.
I know.
Yeah.
I was a bit surprised that they didn't make the connection to, say, Borel maps or anything.
Well, yeah. Well, he left set theory a long time ago and switched to computer science.
And this guy, he is a colleague of David Chodonsky.
Who? David who? Oh, Chodonsky. Oh, yeah. You said his name. You said his name properly, so I didn't know.
Yeah. Sorry. And actually, I got into contact with him a little bit. He sort of appreciated what I did to their paper.
What I remember about Shai Ben David most is, like, I used to call him not so Shai Ben David, because I was at a conference with Bev Diamond and he was hitting on her constantly.
Okay, but that was the entertainment for tonight.
That was good. That was good. That was good.
The afternoon.
Klaus Peter, I have a question.
Yep.
You familiar with the papers by Dick Hodell's student named Charlesworth? It's his last name. I forget his first name. He wrote about translating some of these Gödel theorems in mathematics over to computer science. And so that's the title of that, your paper, Machine Learning and Computer, reminded me of his paper. So I didn't know if you would look at that or not.
Charlesworth, did you say, like so?
That's the last name, Charlesworth.
His first name is how much?
I can't remember. John something. Yes.
I just Googled and found an Ian Charlesworth.
Oh, Ian.
Maybe it's him.
I'll have a look on MathSciNet to see what's there. So, but anyway, the thing that really got my goat in the beginning was this guy writing about the continuum hypothesis being a paradox.
Yeah.
What?
Well, from some point of view, it is a paradox. Yeah.
Well, come on. And also, I think, but this Pavel Rubesh, he wrote to me about, there were some things in that in this paper that seemed to suggest that even, even that connections to the incompleteness theorems of Gödel. Yeah, okay, it shows an incompleteness in set theory, but this Rubesh guy, he wrote to me that there was some, let's say, interference by the editors of the journal who tried to spice up the paper by
Were they aware of
inserting maybe some spurious
claims? Yeah, making it more saleable. Yeah. Were
I
they
think so.
were they aware of Kuratowski's work?
Not that I know.
Oh.
Well, they don't refer to it anyway.
Oh, I see. It's a very short paper, 5 pages. Eh?
This one, yeah.
Yeah.
But they pack a lot of stuff in it because they use a 2 or 3 column format.
I see.
And the letters are not that big. So the information density is quite high. And Kuratowski's paper, I think, is only 3 pages in Fundamenta. And before it, there's a paper by Sierpinski on this type of thing with respect to the continuum hypothesis. And after Kuratowski's paper, there is one by Sikorski, where he generalizes the idea of Kuratowski for higher cardinals. You can take this decomposition thing and you can okay, so Kuratowski had those finite sections, but you can also look at countable sections and sections of size LF1 and so on. And you can characterize all types of successors of cardinals in that way. Because omega 1 can be split into 2 sets that are horizontally and vertically countable, but you cannot do that with omega 2. So you can write characterizations of the first few cardinals in that sense as well. So anyway, that particular issue of Fundamenta has those 3 papers in a row that keep generalizing each other.
KP, I have
Okay,
2
well,
questions. One is mathematical and the other is mundane. Mathematical, you have this continuum hypothesis with each point having being differentiable, the function being differentiable at each point in one of 2 directions. And the question is there any characterization of the points where you get it vertical? I mean, there's 3 sets here involved here: vertical but not horizontal, horizontal but not vertical, and in both directions. Do they have any idea what those sets look like?
They probably do, but I don't. Because just when I was preparing this week, I realized that there was this connection. I said, okay, let's mention it, but I didn't go into the details because there was some, here and there was some heavy descriptive set theory going on. At some points, I think they even need some uniformization here and there, but still at Borel level, I think.
It might be a good
Okay,
thing to look
and
into.
the mundane question.
Mundane question is, where does the word learning come in? I mean, what's the motivation for using the word learning? Learning function.
Well, it's the buzzword of recent years, machine learning. it's learning in the sense that I think the program collects tons of cases where something goes wrong and something goes right. And eventually, whenever it meets a situation, it very quickly compares it to the whole database of situations that it found and say, oh, it looks like this one, and that went okay. Let me try this. And that's the learning that's going on. I think the program that beat this Go Master a couple of years ago, if you recall that.
Yep, we recall.
And that was basically a program that was turned on. It played nearly infinitely many games of Go, collected tons of situations that could occur, and had this learning function that told it what to do, this function that told it what to do in most every case. And it had amassed so many cases and possibilities that it was able to beat the Go Master simply by being able to very quickly pick out an optimal thing. There was no strategy behind it. It was just brute force seeking all kinds of possibilities. That's what I understood from the description of it anyway.
Yeah, from something I read a while back when this was big news and recent news, was that the people, this was the world champion Go player, but there are some other very good Go players who are more strategically oriented than this world champion. And they said, we have a, it's a more, they're more spatially, how shall I say, sophisticated, and they would have liked a chance at this.
I didn't read, but that's what I gathered from reading up on a few of those things, is that it didn't develop strategies, but it simply developed many possible ways of reacting to situations.
Yeah.
And well, if you call that learning, fine.
Yeah. Yeah, the reason I'm interested in this is that I was a fairly good Go player, and I caught on to things. I mean, tactically, I wasn't good at all, but one person after another said, you have pretty good instincts for Go. And I was making a lot of moves just by instinct, and I was being praised for them. My spatial intuition, which is good for topology.
Right. When you probably want to prove every time that the square is two-dimensional.
My temporal intuition tells me it's getting late.
It's only 11:15.
Yeah.
What kind of dimension are you talking about?
Topological dimension.
Inductive dimension, large inductive dimension, covering dimension?
Probably a large inductive dimension, because you're trying to surround things. I mean, you only can surround things if the dimension of the thing is 1.
Right.
Thanks for the talk, KP.
Yeah.
Really enjoyed it.
Yeah.
And yeah, I suppose we'll meet again in about 2 weeks. I am planning on talking again in 2 weeks.
Okay.
So, you know,
Looking forward to it.
Forewarned is forearmed, right?
be warned. Be warned. Yeah, I'm going to continue what I talked about last time I talked. The thing with partitioning stuff into Polish spaces. Last time I showed you how you can do something cool with a huge cardinal. And this time I'm going to show you why you need some kind of large cardinal to do that cool thing. So anyway, y'all have a good
Alrighty.
weekend.
Thank you.
Bye, everybody.
Have a great weekend, everybody.
Easy on the eggs.
He's in.
Oh,
Oh, it's Easter.
and
right?
happy Easter.
Right.
And we already had a day off. Good Friday is a day off here,
Not for
as
us.
is Easter Monday. So we have a very long weekend.
Yeah.
We,
Easter Monday used to be a day off for us, but somebody who was one of our presidents, who was an elder in the Presbyterian Church, decided no more. And so students can't, even in pre-COVID days, that really cut down on the ability of students to be with their families for Easter.
Yeah, well,
okay.
I actually have the power to end this thing.
Well, we can all end our own thing. Oh, power button. Here you go.
Okay.
All right. Good to see you.
See you,
All right.
see you in
Thanks
2
a lot.
weeks.
Yep.
Bye-bye.
Bye-bye.
3, 2, 1, end. There you go.